start. Can you see the screen?
No, doctor.
Not visible. Just a second. Now, is it visible?
Yes, doctor.
Okay. Okay, so today we will start with the wavelet transformation. Okay, so just like a Fourier transformation, this is the another transformation, that is wavelet transformations. So basically, why there is a wavelet transformation? Because there are some limitations of this Fourier transform. Okay, now we know that the Fourier transform, how we represent the discrete Fourier transform. So we write the Fourier transform like this: f of u is 1 by n, the summation from 0 to n minus 1 f of x e to the power this term. Okay, and inverse Fourier transform we write like this. Now here we are having this component e to the power j 2 pi ux by n. Okay, so u is the limit. Most of the time we use n here. Okay, small n and capital N. So the Fourier transform reveals the which frequency components are present in the given function. Okay, so the Fourier transform talks about the frequency components. Okay, for example, if I want to plot, suppose I'm having f1 of t, which is cosine function of 2 pi phi u t. Okay, 2 pi ft. Here, this phi u is the frequency component. I will write this. This is f1. Say this is f1. Okay. So the representation of this cos 2 pi phi u t is like this. Okay. So one time period is 1 by 5, that is zero point 0.2. Okay. Time period I can find out with this. Suppose I'm having the second frequency function f2t, which is cos of 2 pi 25t. Here the frequency is 25. And if I plot this, this will look like this. Okay, the magnitude is 1, the frequency is 25, so the time period of one cycle is 1 by 25. Okay, the third is third function cos of 2 pi 50t. It will look like this. Okay, if I plot from 0 to 1, the time period from 0 to 1, you can see how many total cycles are there. If frequency is more, then more number of cycles will be there. Okay, so if I find out what frequency exists for this waveform, so I will get this. Now here you can see the frequency is phi u. You are getting phi u here. Now for this, if I find out the frequency, so you will get here 25. You can see the peak at 5, peak at 25, and this is for the 50 hertz. So you will get peak at 50 hertz. Okay. Now, in Fourier analysis, if I combine this, because Fourier analysis says the what type of frequency, how many frequency components are present in the given function. Now, if I combine all these three waveforms, f1, f2, and f3, and if I generate the function f4, which is combination of this three, and if I plot this, so it will look like this. Okay, and if I want to find the frequency component present in this signal, so you will get the Fourier transform like this. Okay, I can find the frequency component of the given signal using Fourier transform, and you will get the Fourier transform like this. So you will get 5 hertz frequency is there, 25 hertz frequency is there, and even 50 hertz frequency is there. It is correct. Okay. So this capital F4 of U is nothing but the Fourier transform of F4 of t, small f4 of t. Okay. Small 4 f4 of t, I'm applying the Fourier transform on this and I'm getting capital F4 of u. Okay. Now, the limitations of this Fourier transform, if we see, so I'm having this signal. Let us say this is the given signal. Okay. And I'm getting the Fourier transform like this. Okay. Now, in this case, it cannot provide the simultaneous time and frequency localization. Okay. So, it is having poor localization in frequency domain. This is having poor localization in frequency domain. And this Fourier transform is having the great localization in frequency domain. Okay. So basically what Fourier transform do, so it gives information about only about the frequency, not about the time. Okay. Simultaneously we cannot localize time. Okay. Now the second limitation is it is not very useful for analyzing time variant non-stationary signals. Okay. Now this given signal, which is combination with frequency 5, 25 and 50, this is the stationary signal, which is non-varying with frequency. You can see it is same throughout 0 to 1. Non-stationary signal will look like this. From 0 to 1, you will see the difference in the waveform. Now, difference in the waveform means from this to this, you will see different frequency. From this time period to this time period, you will see different frequency. Period, you will see the different frequency components. Okay, though the magnitude is same one, but the frequency throughout this time is changing. Frequency of the signal is changing. That is varying frequency. Okay. This is non-stationary signal. Okay. Here in the stationary signal, we will be having the non-varying frequency. Okay. So this is our F4 signal, F4T. And this is our, let us say, non-stationary signal, F5T. Okay, which is look like this. Okay, so you can see here this is the component of 5 hertz, this is 25 hertz, and this is 50 hertz. Okay, so it is not very useful for analyzing time varying non-stationary signals. Fourier transform is not useful. Now if I apply the Fourier transform on this given signal, so I know I will get this. Okay. But if I apply the Fourier transform on this non-stationary signal, which is varying with frequency, throughout this time, frequency of the signal is varying. So varying frequency signal it is. Okay. So you can see you will get Fourier transform like this. Okay. Now, in this case, the three frequency components like this, you are getting somewhat similar to this. Okay, because this is varying frequency throughout time, but you are not getting sharp peaks here. Because why? Because this waveform is not same throughout from 0 to 1 second. Okay, so the three frequency components are there, but they are not present at all time. Like these three frequency components are present at all times. Okay, in case of this. So this capital FIU is nothing but the Fourier transform of small FIUT. Okay, so I'm getting this type of Fourier transform with the non-stationary waveform, which is having varying frequency component. Okay, okay. Now there is a perfect knowledge of what frequency exists, but no information about where these frequencies are located in time. Okay, now in this case, for the non-stationary waveform, you can see the 5 hertz frequency basically is only from this time to this time. This 25 hertz frequency from this time to this. 50 hertz frequency exists between this time. Okay, but it cannot give us the information about these frequency are localized in during which time period. Okay, so that information is missing with the Fourier transform. Okay, so this is another drawback of this Fourier transform. And the third drawback is if I apply the Fourier transform on this type of image, so I will get this this function, this profile of this image. If I apply on the image, so it is not efficient for presenting non-smooth functions. So this type of the Fourier transform basically not efficient for representing the non-smooth function. Okay, you can see here what type of profile you are getting from this image. Okay. Now, if I apply with Fourier transform on this profile of this profile of the image is at this location, this line, red line location. If I apply this Fourier transform, so I will get the very sharp corners in the output. Okay, so and somewhat discontinuities also be present in the function. So this is also another drawback of the Fourier transform. Okay, so these many drawbacks we are having uh, in this Fourier transform. So we can list out these drawbacks like this. So Fourier transform is that it has a high resolution in the frequency domain, but zero resolution in the time domain. Okay, it can tell us exactly which frequencies are present in the signal, but not at which location in time these frequencies have occurred. This information is not there in the Fourier transform. Different in time but same frequency representation. Fourier transform only gives what frequency component exists in the signal. It cannot tell what time the frequency component occur, and the time frequency representation is needed in most of the application. Okay, so in that case there is the another transform we will be using which gives us the information about even time localization. Okay, so the wavelet transform basically gives us information about that. Okay, now what are the criticism of this Fourier spectrum? So the Fourier spectrum basically gives the spectrum of whole time series. Whole time series means from minus infinity to plus infinity. Okay. So which is okay if the time series is stationary, because in stationary case throughout time the waveform is same. But what if it is not stationary? Okay, so we need some technique which can march along a time series and that is capable of analyzing spectrum content in different places. Different places means the different places in the time axis. Okay, and which detecting the sharp changes in the spectral character. So this is important in many of the applications. And for that, uh, now firstly, to overcome this drawback of this Fourier transform, the short time Fourier transform is there, which is the advanced version of this Fourier transform and which gives the information about the time localization. Okay, to overcome this drawback of the Fourier transform, this came, okay, that is short time Fourier transform, which is STFT. Now, what this short time Fourier transform do? So you can see I'm having this non-stationary waveform. This is FIUT waveform. Okay. Now, in the short time Fourier transform, it's TFT, this segment the signal into narrow time intervals. Segment like this, you can see this orange box. Okay. Now, why this orange box is from this time to this time? Because you can see between this time, you are seeing that the waveform is look like a stationary waveform. Correct. The frequency is same. So in STFT, it segments signal into narrow time intervals, and the narrow enough, this time interval should be narrow enough to be considered stationary. Okay, and then it will take the Fourier transform of each segment. Okay, now each Fourier transform provides the spectral information of that separate time slice. Okay, so I can slice this total non-stationary waveform in three, like here to here, here to here, and here to here. Okay, so each um, slice will give us the Fourier transform, which provides the spectral information. Okay, now here we can get the uh, simultaneously the time and the frequency information using this STFT. Okay, now the steps involved in this process is, first thing is we need to choose the window of finite length. The second step is to place the window on top of the signal at t equal to 0. Okay, so first thing is we need to choose a window. So in the last lecture, the previous lecture, we have seen the windowing technique. The same technique we will use here. So the window, we need to choose the length of the window. Then that we need to start from t equal to 0. Okay. Place that window at t equal to 0. Then truncate the signal using window. Then compute the Fourier transform of this truncated signal and save the result. Okay, this is as simple as that. Now the incremental slide, again this slide, this window we will move forward, that is will slide the window towards the right, and then again we will truncate the signal using this window. Again we will apply the Fourier transform on the truncated signal, and then again we will save the result. Okay, so this process we will do until it reaches the at the end of the signal. Okay, reaches up to 1. Okay, so this is how the STFT process is done. Now, mathematically, if I want to represent this short time Fourier transform, so I can write like this: STFT of this T dash U. T dash is the time parameter. U, this whole thing is the frequency parameter. This is basically integration over time T. F of T is the given signal f of T, and into capital W T minus T dash. Capital W is nothing but the windowing function, and T dash is centered. T dash is basically the time parameter, the time at which this is calculated. So we can say the length of the window. Okay. So this T minus T dash, this is calculated. This window function will centered at T dash here. This into e to the power minus J2 pi ut dt. Okay, this term is integrated over total time period T. Okay, so like this we can write the STFT representation in the uh, mathematical form. Okay, so then I can get the time and frequency spectra like this. So suppose I'm having the signal like this, which is having this amplitude and this varying with respect to time. So I can choose the length of the window, and then I can find the Fourier transform. And for this time, suppose I will get this frequency. For this time, I will get this frequency. Like this, I can plot the spectra of the whole signal. Okay, so this is one of the technique for the to find this STFT components, that is to get the information of the time spectra and the frequency spectra simultaneously. Okay, now in this case, the drawback of this is the window size will be same throughout the calculation. Okay, but in some application it is again not required. Okay, so this also should be changing the time duration, the window. Okay, now if I want to show the Fourier analysis and the wavelet analysis, if I want to compare how it looked like. So the Fourier analysis is based on the indefinitely long cosine waveform of the specific frequency like this, and the wavelet analysis is based on the short duration wavelet of the specific center frequency. Like you can see at this center for the short duration it is there. Okay, now basically what this wavelet means. So the wavelet, if I say the definition of this wavelet, so the wavelet is the mathematical function used to divide a given function or a continuous time signal into different scale components. Okay, So this comes from the word wave, wavelet. Wave, we know that the wave. Okay, so the wavelet is basically the mathematical function is used to divide a given function or the continuous time signal into different scale components. Okay, this wavelet transform is basically the representation of function by wavelets. The transform is the representation of a function by the wavelets. Now, this wavelet transform has small frequency values, a high resolution in the frequency domain, and low resolution in the time domain. For small frequency values, it is having high resolution in frequency domain and the low resolution in the time domain. And for the large frequency values, it is having low resolution in the frequency domain but the high resolution in the time domain. Okay. Now, if we see what are the advantages we are having with respect to this wavelet, so so it basically provides a way for analyzing waveform in both frequency and the time duration. The representation of the functions that have discontinuities and the sharp peaks we can get here. We can represent the given signal into the representation with discontinuities and the sharp peaks. It accurately deconstructing and reconstructing finite, non-periodic and non-stationary signals. It allows signals to be stored more efficiently than the Fourier transform. Okay, so there's many advantages we are having with the wavelet transform. Now, if you see the history of this wavelet transform, so basically it is started in 1909. The scientist Alfred Haar. So he has first discovered this wavelet theory. So he has done his doctoral research in that. Okay. So it started from this 1909 till date. We will be seeing the many advancement in this wavelet transform. Okay. So you can see the development of this wavelet transform like this. So the main motivation behind this wavelet transform is like we have compared these two signals F4T and F5T and we got the spectra like this, frequency spectrum like this. Okay, so some signal obviously have the spectral characteristics that vary with respect to time. So we need to find out the frequency component, the particular frequency component which are localized in which time duration, during which time duration. So that information is needed and that I can find with the wavelet transform. Okay. Now, for example, if I take the real-time example for the motivation, like if I know, like this is the non-stationary waveform or the dynamic waveform, which is changing with respect to time. So the more non-stationary dynamic signal, uh, we will get in most of the application very worst signal, very worst this signal. Okay. Now this bad signal, it is non-stationary in nature. Like we can take the example of ECG waveform, like ECG signal, or you can take the stock market prediction signal, or some sensory data from some equipment. If you get some data using sensor, that is also like a very dynamic signal you will get. Okay, so in real life if you see, so there are many signals which are non-stationary in nature. If you see, you cannot identify the what frequencies are there exist in the signal. Okay, now to analyze this dynamic signal, a much better way is we can use the wavelet transform instead of the Fourier transform, and then we can analyze that signal in much better way. Okay, so this wavelet transform is basically very powerful tool for the analysis and even the classification of the time series and the signals. Okay, so many of us we know that the Fourier transform only, but wavelet transform is widely used in many of the research. Okay, in many biomedical applications it is used, in even in the data science it is used, the wavelet transformation. Okay, now the time and frequency resolution, because the thing about the Fourier transform is that is it has a high resolution in.
Doctor.
Hello,
The slide not visible.
slides are not visible, just a
Yeah.
second. It was visible earlier or not? It has gone now, or when it has
Still
gone?
not.
Just now. Now can you see the
Okay.
screen? Is it visible now? Screen?
Yes, doctor.
Okay. So the thing about this Fourier transform is that uh, it has a high resolution in the frequency domain, but the zero resolution in the time domain. Okay, this is the frequency axis and this is the time axis. Okay, now for FT we are having more resolution in the frequency, so I can divide this frequency spectra, but poor localization in the time spectra, time domain. Okay, that means it will only it gives the information about the frequency, what which frequency is which frequencies are present in the signal, only that information it will tell. Okay, now you can see in time series we will get only the time spectra. In the Fourier transform we will get only the Fourier spectra. Now this is the short time Fourier transform where we will get the time and frequency spectra, but you can see the window is constant, the length of the window is constant. Therefore I can get the information with the only constant window length. Therefore you can see each block is having same size, but this is not the case in the wavelet transform. Okay, in the wavelet transform you can divide this like this. Okay, so you can divide your time for different time duration, you will get different frequencies. So like this we are having the wavelet transform. Okay, so time frequency resolution with the different methods. So these are the different methods we are having for the time and frequency resolution, that is time series method, Fourier transform, short time Fourier transform, and the wavelet transform. Okay. Now, in this case, how this wavelet transform works. Okay. So, the Fourier transform uses a series of sine or cosine waves with different frequencies to analyze the signal. That is, the signal is represented through the linear combination of the sine waves with different frequencies. But if you see the wavelet transform, it uses a series of functions which we call the wavelets, and each function with a different scale. Okay, so the word this wavelet means a small wave, and this is exactly what the wavelet is. Okay, this is combination of small waves, you can say. So this is the wavelet. So you can see this sine wave is basically infinitely long, but the wavelet representation is like this, which is localized in the time. Okay. So the difference between the sine wave and the wavelet you can see here in the figure. Now the main difference is that the sine wave is not localized in time. So it stretch out from minus infinity to the plus infinity, while the wavelet is localized in time. So this allows the wavelet transform to obtain the time information in addition to the frequency information. Okay. Now, in the wavelet transform, the wavelet is localized in time. So we can multiply our signal with a wavelet at different location in time. Okay. So can we can start or we start with the beginning of our signal and slowly move the wavelet towards the end of the signal. Okay, so basically there we do the convolution. We multiply the wavelet which is localized in time, okay, and that we multiply at different location in time. So we basically do the convolution. Okay, now in this procedure, basically this procedure, uh, so there are some mother wavelet present. Okay, so these are the most popular mother wavelets, and we can scale it such that it becomes larger and repeat the process. Okay, so the most basic mother wavelet is Haar wavelet. Okay, so the scientist Haar, which has started this wavelet transform theory, so his name is given to this wavelet. So this is very popular and the basic one, which is Haar wavelet. Okay, the representation you can see here like this. The other is Shannon and Singh type of thing. This is Debach's 4, Debach's 20, the Gaussian, bio orthogonal, Mexican hat, Wavelet. So these are the some of the popular mother wavelets are there. Now, in this process of wavelet transform, if I see the principle, so we can write down the wavelet transform. So basically, we are having the continuous wavelet transform and the discrete wavelet transform. Okay, so the continuous wavelet transform is uh, written like this. Okay, so this CWT is continuous wavelet transform. This is for signal x of t, and this psi is the mother wavelet. Psi is basically the mother wavelet. Okay, so continuous wavelet transform for this x of t signal using this mother wavelet from this time tau and in the s domain. This is s is nothing but the scale we are doing here. So this is equal to, this is also written like this, capital psi x of psi. Tau is the translation, that is localization of the window, and s is the scaling factor s, which is equal to 1 by under root of mod of s, integration of this x of t signal. This will convolve with the psi star, that is mother wavelet function, conjugate function, which with t minus tau by s into dt. Okay, so this is how we represent the continuous wavelet transform. So you will see here the mother wavelet is important here. With the help of mother wavelet, we do this transformation. So we can, I can choose any of the mother wavelet as per the requirement, as per the application. Okay, and for each mother wavelet, there is also this psi is mathematically written. Okay, and the very simplest mother wavelet is Haar wavelet. Okay, now this wavelet, we know that this is the small wave consisting of the small wave. The window function is a finite length. Okay, the length of the window function is with this tau. Tau is for the length of the window function. Okay, now the mother wavelet here used is a prototype for generating the other window functions. So all the used windows are its dilated or compressed and shifted version. Okay, so like if I take that example of image, if I am doing the image processing, so on the image I can dilate the image, I can compress the image. Okay, so I can do this with this. Okay, the wavelets. So if I choose the proper window size, so with that, I can dilate my image, I can compress my image. Okay. Now the steps to compute this continuous wavelet transform is like this. Now I know that first thing is I need to choose the prototype or the mother wavelet. So for each mother wavelet, it has its own equation, and that is known to us. Okay, and the signal, the given signal, suppose it look like this is the given signal. Okay, now the step number one in computing this continuous wavelet transform is take a wavelet and compare it to the section at the start of the original signal. So this is the start of the signal. And calculate a correlation coefficient C here. Okay. Take a wavelet means take a mother wavelet and compare it to the section at the start of the signal, original signal. So we need to again choose the size of this window and calculate the correlation coefficient, what coefficient you will get here. Okay, so I can apply this formula and I can find out that. Okay, now the second step is, then till now I have done in the step number one. Second step is shift the wavelet to the right and repeat the step number one. Okay, so I will repeat this and I will find the wavelet like this for this duration. Okay, the step number three is stretch the wavelet and repeat step one through two. Okay, again I need to stretch this and again I need to find the correlation coefficient here. Okay, so this I will do till the end of the signal. So I will repeat step number 1, 2 and 3 for all scales till the end of the signal, and then I will find the wavelet. Okay, this is how in simple way we can say the wavelet transform works. Okay, so the continuous wavelet transform is like this. This is the formula. This is the formula where this psi star is 1 by this. And the discrete wavelet transform, if you see the formula, this is in discrete case, we are having summation here from 0 to n minus 1. X of m is the given sequence. This is multiplied with this psi conjugate of j m minus n here. Okay, here t is basically t minus 2 by s. S is the scaling factor here. Okay, now in this case, the scaling factor is a in the discrete domain. Okay, so this is for discrete way, we will be having the samples in the given sequence. So it is with n and a is the scaling factor here. Okay. Now the most basic wavelet, the mother wavelet we will see now, that is the Haar wavelet. Okay. Now this Haar, the mathematician Haar has proposed this wavelet Haar transform in 1909. Now the Haar wavelet is basically a sequence of rescaled or square shaped function which together form a wavelet family or basis. So in this figure you can see these Haar wavelet is basically look like this square function. Okay, now this, if you see this Haar transform or Haar wavelet, this wavelet analysis is similar to the Fourier analysis. Now in that it basically targets the function over an interval to represent it in terms of the orthogonal basis. Now this Haar sequence or the Haar transform is the first known wavelet basis. This is the first known wavelet basis and is extensively used as a uh, in many application as a basis. Okay. Now this har used these functions to give an example of orthogonal system. Like if I want to write this har mother wavelet as a function, so I can describe this har wavelet in the function psi of t like this. This is the mother wavelet function, that is psi of t. So if you observe how this har wavelet is, so from 0 to 1, from 0 to half, it is 1. From half to 1, it is minus 1. Otherwise, this is 0. Okay. So in a simple way, this har mother wavelet function psi of t is written. So from time 0 to 1 by 2, it is 1. From 1 by 2 to 1, it is minus 1. And it is 0 otherwise. Okay. So if I want to scale this, the scaling function is, if I want to write the scaling function here, so this psi of t, I can write it is 1 from t 0 to 1, and otherwise it is 0 if I scale this. Okay, so this is very simple uh, mother wavelet. Now, for example, if I'm having signal like this, suppose I'm having signal like this. Okay, so what this har wavelet do? So it divide this signal in this two. Again, this two is divided like this. Okay, now from this to this, if I localize this here, so this is positive and this is negative. Now, if I do the average of this, so I will get this type of thing. Okay, so whatever positive region I am having here, the same negative region I will be having here. So such type of uh, division we need to do in this Haar transformation using this Haar mother wavelet. Okay, so this is very basic Haar wavelet, and in most of the image processing techniques it is used. So that is basically represented in the in terms of the image representation. Okay. So in your syllabus, that much deep we will not go. So therefore, I have not written that the transformation matrix and all. So just the simple idea of this hard transform is like this. So we can get the localized information with this squared function. Okay. And we'll do the averaging and then we'll get the information about that. So this is the wavelet transform. So you can see there are many applications where this wavelet transform is used, like in audio compression, the speech recognition, image compression, video compression, the biomedical application you will see. the motion detection and tracking system also you will see this wavelet transform is used. Okay, so this is about the wavelet transform. So basically, I have not gone much deeper in the wavelet transform uh, formulas and the mathematical equations. Just this is just an general information of this wavelet. Okay, so in DSP, basically this is the entire different topic. Wavelet transform, the multi-rate DSP. This is entire different topics. And nowadays there is more advancement in that. Okay, so this is this wavelet transform. Yes, do you have any doubt in this?
No, doctor.